We are going to continue our discussion on maxima minima for functions of 2 variables and 3 variables, and we are going to introduce to you a new method in this topic. Okay, and this method is called the method of Lagrange multipliers. Okay, so just recall that in the previous lecture, okay, let me see if I have this. Yeah, so in the previous lecture we had this example. Okay, so let me just go back. Yeah, this one, where we had a function of 2 variables. Okay, and what we were trying to do is we were trying to maximize or minimize this function for this on this domain. Okay, so now this domain had the interior and its boundary, correct? So we had a picture also. So this was the domain. So we needed to find maximum and minimum values of the given function inside as well as on the boundary. Remember? So now you know what we did, that for each of these boundary lines we dealt with this question of finding maxima minima separately, and then we saw that on each line we got a function of one variable and then we solved it for a maxima minima and then we compared the values, isn't it? So this was the situation where we tried to find the maxima and minima on some particular lines. So that means when the points are varying on some particular lines. So this example or this situation, one can ask the following question in general, that suppose I want to do this, that I want to find the extreme values of a given function. Okay, this can be in 2 variables, it can be in 3 variables also, and subject to a constraint. Okay, so this is the English term for the the constraint on the variables. So these constraint on the variables, for example, the sides of a rectangle, they can be thought of as some curves, and hence they will be given as a level curve of a function. Okay, and here when you are in 3 variables, it will become a level surface. Okay, so imagine that instead of calling it the side of a rectangle, we say that this is the curve on which I want to find the maxima and minima of our function. Okay, so this is the most general situation for this kind of questions, that I have a function and I want to maximize or minimize or find its extreme values, subject to the condition that variables, they lie on a given curve. Okay, now this curve can have along with it a domain, or it may not have. The problem could be just to maximize and minimize the given function on that level curve or level surface. Okay, if you are in 3 variables. So this is the situation which we will try to answer, and the method is referred to as the method of Lagrange multipliers. Okay, all right. So just consider this situation. Let's say we are in 2 variables and we want to maximize or minimize f subject to the constraint given by this. Okay, so what is going to happen? We are going to have this kind of situation. Okay, so we want to find the maximum and minimum values of f when the points lie on this curve. Okay, so as you can see, this is going to happen. For example, the maximum is going to happen when the level curves of f, they meet the level curve which is given by g at a point. That means they touch each other. Okay, if they don't touch each other, then you will see that the maxima or minima will be shifted. So we have to look for another level curve of f accordingly. Okay, so this maximum is going to be at a point where these two guys meet. Okay, now how does it translate to math symbols and in the terms of gradients and so on? So just recall the definition of gradient. What will happen at this point of intersection? These two level curves, they meet. The gradient, if I compute for f and g, then we know that this is going to be the normal vector. Okay, and they are going to be having the same direction, correct? The gradient of f and the gradient of g, they will have the same direction. Okay, or in other words, they are parallel. So when that happens, I can express one in terms of as a scalar multiple of other. Okay, so this is what it is. So there is going to be a lambda such that the gradient of f is lambda times gradient of g at this point. Okay, so here we have assumed all these things, that the gradients they exist, and then the maxima and minima they exist for the function. Otherwise, this problem doesn't really make sense. Okay, so this is going to give you an equation, correct? Because when I have compared these two things, so if I compute the partial derivatives, I equate them with this lambda parameter, we are going to get an equation. Okay, so this is this idea gives rise to this method of Lagrange multipliers. Okay, and this is how we are going to basically apply this method. Okay, so let us say, yeah, as I said here, I mean, we are going to do this with some examples. Okay, and these examples sometimes will be for functions of 2 variables, sometimes they will be for functions of 3 variables. Okay, so as always we do, and if I am writing a definition for 2 variables or 3 variables, the corresponding definition should be written for the other part. Okay, all right. So let us assume that we want to find extreme values of this a given function subject to this constraint. Okay, now I am talking about 3 variables. Okay, because I just explained things for 2 variables, and let us now write it for 3 variables. Okay, so we need to assume, as I said, that the extreme values they exist, and the gradient is non-zero. If it is 0, then we don't do anything. Okay, so because we will not get any constraint equation. Okay, so so this is the level surface. Okay, and I am saying the gradient is zero, non-zero here. So how do we find the, okay, so this is constraint. Okay, there is a t here. What you do is first compute the gradients. Okay, or in other words, you compute the partial derivatives of f and g, and then consider this equation. This was the equation for the maxima minima, because at that point where they touch each other, the gradients are parallel, so you have this relation. So you do this. Okay, so you basically do it for a lambda, and the equation of constraint is given to you. Okay, so what you have actually got, you have got, now these are the 2 vectors. So you have, when you put them equal, what you are going to get 3 equations, correct? Because vectors, they have 3 components, so all the 3 components have to match. So there are 3 equations over here, and there's one more equation over here. And how many variables we have? We have 3 variables and then plus 1, this lambda parameter. So we have 4 equations and 4 variables. Okay, so what we do is we try to solve this equation. Okay, so like we do for critical points. So we solve these equations and we find the points x, y and z. Okay, and all we need to do is we basically evaluate our function at these points, because these are going to be the points. If you remember the picture, that point of intersection, that is where this relation is happening. So I am going to get a point, okay, or the coordinates of that point. So there can be more than one point. So we just need to evaluate our function at these points and then compare the values. Okay, so this is how we are going to apply this method. So let us do a couple of examples. Okay, one example we have already done, that example of finding extreme values over a rectangle. So I am going to give you another example, so that you have more than one type of examples, and then you can solve the previous example using this idea. Okay, so let us look at this example. So here the question is that find the absolute maximum, okay, of this function, and the domain is given. Okay, so this is precisely the situation which we have already dealt with in the previous example. Okay, so only thing is the domain is, instead of a rectangular domain, it's a disk type domain. Okay, so this is again a closed and bounded situation. So the method of Lagrange multiplier, if you look at it straight away, then what we expect a function and then a level curve or a level surface. Okay, whereas this example is not really a level curve or a level surface. This is a domain in R2. Okay, so what we have to do is we have to apply our method. How do we find the absolute maximum or minimum of a function on a closed and bounded domain? Okay, so in the interior part, when we do it as usual, but when we come to the boundary, okay, now we have this additional method with us. Okay, when we discussed the example of the rectangular domain, we did not have this method. So we did it on each line by hand separately. But now if I just look at the boundary of this, which is going to be the circle x square plus y square equals to 4. So this is a level curve in a way, correct? So I can apply the Lagrange multiplier method, okay, to the boundary. So this is how we have to try to see that which method is applicable. Not only that, we have to also see that which method easily gives the answer. Okay, now that can come only with the practice. There's no fixed rule that you apply this method or that method. So it depends on the example, it depends on the constraint, or it depends on the domain, and so on, various factors. So if you practice enough, you will be able to see that, okay, here I just apply this. Okay, so for example, even in this example, if I ask you to find absolute minimum, what will happen? Look at this function. There is an x square, there is a y square, and the domain is a disk which contains the point 0, 0. So without anything, you will be able to see that the minimum is going to be 0 only at the point 0, because when x and y, one of them is non-zero, the value is positive. So we have to be careful. Sometimes we have to apply intuition, sometimes we have to just evaluate the function at certain points. When example becomes a little complicated, you reach out to these methods. All right, okay. So as I said, we will do it in two steps. First we will find the extreme values in the domain, and then we go to the boundary. Okay, so this is a slight typo here. The boundary is not equal to 1, rather it is equal to 4. Okay, so please correct that when you solve it. Okay, so okay, and I mean, again, I can do this, or we can try to do this problem by the method which we applied for the rectangular domain. Convert the function into a single variable function on the boundary, and try to find the maximum minima. But rather we will illustrate it using the Lagrange multiplier. Okay, so let us do it. Step 1, as usual, we just find the critical points. So you compute the partial derivatives, set them to 0, and here this is a simple situation. Here 8x equals to 0 and 20y equals to 0, so the critical point is just 0, 0. Okay, and evaluate the function at that point, so you get the 0 value. Okay, and certainly 0 cannot be maximum, because the function is non-negative all the time. Okay, so now we go to the boundary. Okay, yeah, so here I have written it correct. So the boundary is given by this circle of radius 2, and this is precisely the situation which the method of Lagrange multipliers address, isn't it? So I have this function and I have this level curve. So I consider this equation. Okay, set the gradients with this parameter lambda equal, and try to solve. Okay, so when I compute this, I knew that this was 8x and this was okay, I mean, you can look at over here. So yeah, I did not write this equation, but I have written the second step here. So the gradient of g is going to be twice x, so then there is a lambda here. So the first component is this, okay, which can be rewritten like this. Okay, so this is twice x common, and then a 4 minus lambda. Okay, so this is one equation from here, and the other equation is this, and the third equation is this one, correct? So now we have to basically solve these things for x and y. Okay, and again you will see that there's no fixed way to solve these equations. Sometimes the equation will be linear, you will solve it easily. It can be quadratic, it can be cubic, and it can have cross terms. So again, you have to see how to solve the given equations. Okay, so the first equation, for example, is going to tell us that either x is 0 or lambda is 4. Okay, so first look at what is the points we get when x is equal to 0. So x equal to 0, and then we have this equation, so just put x equal to 0 in there, you get that y is plus minus 2. So I have got 2 points, x equal to 0 and y is plus minus 2. Okay, and now the second case, when lambda is 4, so lambda is 4, you substitute in this equation, for example, so this will become 6, So y equal to 0 basically, correct? So I get y equal to 0. Now y equal to 0, again you substitute in the constraint and you get x equal to plus minus 2. Okay, so corresponding to x equal to 0 I got 2 points, and corresponding to y equal to 0, which was the situation when lambda was 4, so I get another 2 points. So the points can be written like this. Okay, and then you just evaluate your function at all these 4 points. So you see that at the point 0, 2, 0, minus 2, the value is it's 40 and the value is 16 at the other 2 points. So the maximum is at these 2 points. Okay, of course you always have to compare it with the value at the step 1 also, but that was trivial because we were trying to maximize a non-negative function, and the value that value was 0. Okay, so we get that the maximum is on the boundary, basically these 2 points. Okay, x equal to 0, so this is going to be the, and this you can intuitively also think, because your function in the y coordinate, it has a larger factor here. It was 10 and in x it was 4. So when y becomes large, this will make it larger, correct? So it was intuitive also, I mean, if you think about it, that the maximum of this should be at the points where y is large. So this is really the extreme point where y is large and x is 0. Okay, so you have to be open and you have to be attentive. Okay, so this was an example which we just solved using the method of Lagrange multiplier. Okay, you try to solve it directly also and see whether two answers match. Okay, so I have one more example for you over here, and this example is okay, for 3 variables. So this is like you want to maximize the value of this function, and the constraint is given by this. Okay, so this is a level surface and you have this function to maximize. Okay, now this often I take examples from the book, but sometimes I also write examples which are not in the book, so don't worry about it. I mean, this is just to get a few more examples. Okay, all you have to do is just do whatever problems you have in the book. Okay, and of course the assignment problems and so on. So don't think that I am following like too many books and so on. I'm just following one book only, like once in a while I get a nice example from some other source, okay, or from some previous lecture notes which I had. So this is I mean, you should not get worried about that. Okay, all right, because examples are I mean, the numbers can change but the method is the same. Okay, so let us see. Okay, and in the book this example is written like this, that this guy, the function f over here, what is it? This is x times y times z. So this is like computing the volume where the sides are x, y and z. Okay, so we are trying to maximize the volume function subject to this constraint, and this constraint is basically, if you think of it, it is nothing but the surface area of a box. But here you see that there are twice and this is only once. Okay, so that means there are only five faces we are considering in the surface. So the example is written like this, that try to maximize the volume of a rectangular box with the constraint that the surface area of this rectangular box without the lid. So basically one face is missing, so that is why only x times y, not twice. Okay, because there are 6 faces and then the opposite faces, they have the same area. So this is how it is. Okay, so we are trying to maximize the volume when the surface area of the box without lid is fixed. Okay, so what is the combination of combination of x, y and z for which we get the maximum area, maximum volume. Okay, this is what the question is. So we just compute the gradients, 2 gradients, and put them in this equation. Okay, and the other equation is given by the constraint. Okay, so you do it. I may make a mistake in these examples, so please be careful. So what I get these 4 equations, 1, 2, 3 and then the 4th one. Okay, so now you see that here the equations are not linear. Okay, so you have to be little more careful than usual. Okay, so we need to solve these things for the points so that we can evaluate our function at those points, and those points are going to be the points of maximum. Okay, as we started with this method. Okay, so look at this. see, I mean on the left hand side I have by z, zx and xy. So if I just multiply everything, all these three equations by x and then by and then z, at least I get that the left hand sides are same, so the right hand sides will be same all the time, correct? So by doing that I get these three equations. Okay, now I solve these three equations. Okay, so here I have written that lambda cannot be non-zero. Okay, why? Because you look at here, if lambda is 0, then by z will be 0, zx will be 0, xy will be 0, so the surface area will be 0. There is nothing to maximize, correct? So this lambda is non-zero. So these kind of things, these kinds of conclusions you have to make depending on the problem. Okay, lambda is just a parameter, it cannot take all possible values. Okay, certain values are prohibited here. Okay, for example, lambda cannot be 0. Okay, and this is not given to start with, this you have to deduce by looking at the example. Okay, so if lambda is non-zero and I can put these two equations together, so xy is common, so this goes away, lambda is non-zero, this cancels out, and then I have twice of zx is equal to twice of by z. Okay, but 2 is also non-zero, so that also cancels out. Now this z is also non-zero. Okay, because if z is 0, if one of the side is 0, then the volume is 0. Okay, so from here we get that x has to be by. Okay, so I get a relation that whatever point I have for x, by is the same. Okay, now you do the same thing, you equate these two and you will get that by has to be twice of z. Okay, so I have got x equal to by and by equals to 2z. Now I have a fourth equation here given by the constraint. I substitute these values over there and I will get that z square is equal to 1. Okay, how is it happening? Let's stare at this equation here. So z equal to 2 or rather x equal to 2z, so this will become 4z square, this will become 4z square, and this also in terms of, so this will become 4z square. So this is 4 plus 4 plus 4, 12, so 12 cancels out and all you get is z square is equals to 1. Okay, so this is going to give me z equal to plus 1. Okay, I have written only plus 1 because I am considering a situation when I am talking about the volume, so the sides cannot be negative again. Okay, yeah, exactly. So you substitute z equal to 1 and then you get these values because x and y are same and they are equal to twice of z, and you know that what is the volume then 2 times 2 is, okay, so this is how we solve. Okay, so you solve a lot of examples. Okay, all the examples where you had these kind of situations, try to solve them by a Lagrange multiplier method. Okay, and this method also has some further generalizations. Okay, so instead of asking for one constraint and the maximum of the function on that constraint, we can also have a situation when we have let's say two level surfaces. Okay, and we want the maximum value on the intersection of those guys. Okay, so that means I can have two constraints. Okay, so that can also be addressed by this method which is referred to as the method with two constraints. Okay, so the situation will be like that, we want to find extreme values of f and the constraints are given by these two level surfaces. All right. Okay, so just try to understand what is going to happen in this situation. Okay, so when we try to do this, that we want to maximize or minimize a given function, what we are saying, basically we are saying that find the maximum or minimum values of f when the points are lying on the intersection of these two level surfaces. Okay, so these two level surfaces, they are going to intersect because now these are the surfaces in R3, so they are going to intersect on a curve. Okay, so let us say that curve is C. Okay, so these two constraints basically are saying that you try to find the maximum and minimum of f on this curve. Okay, so that is why the two level surfaces, they meet on a curve and then that is the curve where you are interested in. Okay, so let us just see that how this thing becomes in terms of the gradient vectors, because they are the ones which are going to give you the equation. So if I have that f has a maximum at some point p, okay, and this point p lies on the curve, then we know that this gradient of f at this point is going to be the orthogonal to this curve. Okay, this is again from the discussion which we had about the gradient of a vector, correct? I mean gradient of a function. So we know this. Okay, so if I have extreme value of f at a point, then the gradient vector is going to be orthogonal to the curve at that given point. Okay, so I have a picture also, I will try to. And now we also know that the gradient of these G and H, because these are the level surfaces, so if I look at the gradient of these two guys, they are going to be orthogonal to the level surfaces. Okay, so corresponding level surfaces, because G has no connection with H. Okay, so the gradient of G is orthogonal to the surface given by G, and gradient of H is orthogonal to the surface given by this, correct? So respectively, it should be respectively. Okay, there are some typos all the time. So but our point of interest is points on that curve, correct? So if these two guys are orthogonal to the level surfaces, that means they are also orthogonal to the curve of intersection in particular. Okay, so what does it mean? I mean, we can conclude that the gradient of f, which was orthogonal to this curve, this has to be on the plane which is determined by these two vectors. Okay, but here we have to be careful. We have to assume that these two guys, they are non-zero. Okay, even if they are one of them is 0, then there's absolutely, I mean, there are no two conditions, and they are not parallel. Again, if they are parallel, then these two surfaces are not distinguishable in a way. Okay, so we assume this, that these two guys, the gradients are non-zero and they are non-parallel. So we can write down the gradient of f, because it lies on the plane determined by these two. So this is going to be this is going to be expressed as a linear combination of these two gradients. Okay, or these two vectors. So which means that I am going to get these two parameters. So in the previous situation we had only one parameter. Now we have got two parameters because there are two constraints. Okay, and we have to take them simultaneously. Okay, so the gradient of f at this point, where the this is going to be orthogonal to the curve, because this is the point of maximum or minimum we have assumed. It is lying in the plane determined by these two vectors. Okay, so this you can express as linear combination. Okay, and instead of one we have now two parameters, and again they are referred to as the Lagrange multipliers. Okay, so look at this picture, for example. This color is G, the level surface given by G, and this is the another level surface given by this H. So what we are interested only on the intersection. So this is a curve which we are writing as C, and suppose at this point I am having the maximum or minimum of f, so then the gradient is going to be orthogonal, and these two guys are orthogonal to this this curve. So this is how you are going to get the plane determined by del G and del F will contain the vector del F. Okay, so this is basically precisely what we have written. Okay, so basically idea is that we want to maximize or minimize a given function, but we are interested in in two situations when the points are lying only on this curve, which is the intersection of these two level surfaces. Okay, so in the previous situation we had only one level surface, and we were trying to look for the maxima and minima. Okay, so that is where we had to find the intersection of level surfaces of f and the level surface given. Okay, but here it is just going to be on a curve. Okay, so again what we can do is we can apply this method in these following steps. So you start with a function and then two constraints. Okay, again you have to assume that the maximum and minimum, or the absolute maximum minimum, they exist for f, otherwise we don't talk about it, and the gradients exist and so on, and they are non-zero, non-parallel. Those assumptions are going to be there, and then as earlier we just compute all the three gradients and look at this equation. Okay, now this equation has two parameters, so you have got one extra variable over here, but that is fine because we have got also one extra constraint, so we have got one extra equation. So now there are 5 variables and there are 5 equations. You solve them for x, y and z, okay, and mu and lambda, and you get points on the curve and just evaluate your function at this point. Okay, so this is how you have to step by step you do it. Okay, and we will give you a lot of examples. Since this is precisely the similar situation, I did not write another example over here, but we give you some examples which you can discuss in tutorials. Okay, so we will give you a couple of examples for this situation also. Okay, and book has several examples. Okay, so I stop here, and in this week you will notice that we have some 10 extra minutes, because these things are connected. If I postpone it to the next week, then because of this recess, we will not be able to talk about it for at least 10 15 days. So that's why I put this extra 10 minutes also in this week. And enjoy your time in the recess, and we will be back after that. See you.